So as mentioned before, today's topic is power topics for 2.5 axis milling. We'll be going through quite a few of these specialized topics that many of you might not be aware of, as well as defining and detailing some of the more advanced concepts in the product. We'll be starting out with the role of tolerances and stock parameters. We'll be discussing that and how you can control tolerances in stock to get the kind of machining you want. Followed by defining work zeros and how to control your machining using work zeros and repositioning your part or your stock model in different places on your work table. Cutter compensation, and then engraving. The engraving method is a very versatile method, and we found that our users use it in many different applications, and so we thought it would be worthwhile to actually go through that and show you how different people or different customers are using it. And then we'll be talking about start points and how to control start points, and also how to control the cutter entry and exits during machining. We'll be also going through bridges and tabs and profiling. And then user-defined tools, how we can create and utilize them. And then finally, fixture offset programming. And it's quite a lot of topics to cover, so without any further ado, Uday, you want to take it away?
Thank you, Joe. Hello, everyone. Hope you're able to hear me. Good morning, good afternoon, or good evening to you all. And thank you again for joining us for this month's AMS webinar series. Today, we will be covering all of these topics as part of our power topics for 2.5 axis milling. And with this, I would like to get started with the actual demonstration and presentation of the product. Now, the first topic we're going to be covering here in today's webinar is the role of tolerances and stock parameters. So first, let's talk about how tolerances will affect your machining, especially in 2.5 axis operations. So tolerance defines or is basically the deviation from your actual geometry. So as you can see from these images on the slide, the slacker the tolerance, the more deviation you will see from your actual part region or geometry, and slacker the tolerance will also have larger chord segments. So the tighter tolerances, as you go tighter, the chord segments will be much smaller, and it will be within the deviation of the tolerance that you specify. Now these affect more when you're using toolpaths outputting as linear segments, when you're working with like polylines or splines. When arcs are not being fit to your toolpaths, the tolerance you can see here has more effect in, as you can see there, there's more deviation from your part geometry. Now you can fit arcs to your toolpaths. Arcs are automatically fit to arcs and circles when you're working with arcs and circles in your geometries. By default, if you have output arcs as linear segments not checked, arcs are fit to the toolpaths. And we'll talk about how the arc fitting tolerance will affect for polylines or polycurves or splines as I go through an example with you. So I'm going to go ahead and switch over to one of our CAM plugin products. In this case, in this example, I'll start with Rhino CAM. We'll also talk about this in our other products as well, as time permits. Okay, so we covered this particular part programming in our previous webinar. So I'm going to use this as an example to cover the tolerances and how it affects in toolpaths. I'm going to switch over to a top view here, and I'm going to be focusing on tolerance in this pocket region. I'll display the toolpath. I have created a pocket operation and left the tolerance as 10 thousandths. And as you notice in these areas with linear motions, with arcs not being fitted to the toolpath, you can see how the tolerance affects around the pocket boundaries as you're programming the pocket, as well as around these island regions. So slacker the tolerance, you'll notice more deviation from the part geometry. So if you want to keep it as tight or closer to the part geometry, you would want to consider tightening up the tolerance. So The next example here I have is where the tolerance is tightened up to 1,000. So tightening it up to 1,000, well, you can see that there's smaller facets and much tighter, much closer within the tolerance of the part region of the geometry for both the pocket boundary as well as the island region. Now the same goes with other two.
Let me interrupt here. One, that was a really good question about the size of the parts that you have. So because that does play into the tolerance settings. So if you can talk a little bit about the size in your slide as well as the parts, that'll be good.
Sure. Thank you. So in this particular example, the part I'm working with is about a little over 7.5 inches by 4.5 inches in X and Y. And the cutter used for these, the tool uses about a 1/2 inch end mill. So also the smaller the part you're working with, the tighter the accuracy, the tighter tolerance will basically maintain it within the deviation from the part geometry as well. Now let's look at how fitting arcs to toolpath will affect the tolerance. So I'm going to go ahead and make a copy of one of these pocket operations here, copy paste. I'm going to go into the preferences, go to machining, and make sure output arcs as linear segments is not selected. And I'll regenerate the pocket operation. And you'll notice that arcs are being fit automatically to the toolpath where you have arcs on the drive or the part region along the model. Now, additionally, you could fit arcs to your toolpaths when you have polylines or splines, and this can be done by going to the advanced cut parameters. You have the option to perform arc fitting and specify the tolerance for arc fitting. Ideally, we recommend setting the fitting tolerance to be set to 2 times of what you set under the tolerance for global parameters. So in this particular example, I'm going to change this to 0.002, which would be 2 times of the global tolerance, and then generate. So this will give you the best result for arc fitting. So where splines or polylines are fit to arcs wherever it's feasible. And the reason we recommend 2 times is to avoid tolerance stacking. So arcs can be fit to toolpaths, and you can specify the arc fitting tolerance. So this gives you an overview of how tolerance affects your machining in 2-axis operation.
I want to jump in here, Uday, and talk a little bit about tolerance stacking. You mentioned that, but I want to dive in a little bit deeper there. One of the things when we do arc fitting, we are actually fitting arcs to the toolpath points. So, I mean, we are looking at just the toolpath and fitting the arc geometry to it. And obviously, when we do that, we have to use a particular tolerance to do it. So this tolerance is independent of your machining tolerance. So in some cases, it might actually introduce some errors because we are using an additional tolerance on top of your machining tolerance. But if you're machining an arc, it's possible that our arc fitting will give you an exact arc. But in some other cases, let's say you're using a NURBS curve, you're machining a NURBS curve, and we fit an arc to the resulting toolpath, that might result in a little bit of an error. So you got to be a little bit careful about these tolerance stacking, what we call tolerance stacking, because you have a machining tolerance. On top of that, you have the arc fitting tolerance. So I hope that makes sense. Thank you.
Thank you, Joe. The next topic we would be covering here is the stock parameters and how this affects in machining in 2.5-axis operation.
Okay, sorry, I want to stop you again because there are a couple of questions about what are the disadvantages of using very tight tolerances. You can explain that.
Sure. So if you're using a very tight tolerance, one of the things you'll notice is you'll have more number of go-to motions. If there are several linear, if the toolpath is being output as linear motions, you'd end up with more number of points, point-to-point moves. So it could be possible on some machines or controllers, the control may not have enough look ahead, and you might see the machine probably could cause stuttering or slowing things down. So as you set the tolerance in this particular example, I'm going to go to the information tab, and you will notice that in the first case, when I set the tolerance to 10 thou, the number of go-to motions is at 607, basically the number of point-to-point moves. And when we tighten up the tolerance to 1,000, you can see it's almost 2.5 times. We have about 1557 go-to motions. And the last one here you're seeing is the arcs being fit to the toolpath. So with the tighter tolerance and it arc fitting, you're seeing about the number of motions is about 2 times. And fitting arcs to toolpaths makes it also smoother and easier on the machine to work with. So tighter tolerance, the more number of go-to motions and more lines of code, which results in more lines of code in your posted G-code or output file. I hope that answered your question, sir. So the next topic I will be covering here is going to be how the stock parameters affect in 2.5 axis machining. So I'm going to switch over to the slide first so we can talk about the role of stock parameters. So stock in 2.5 axis machining or 2-axis machining is a wall stock or an XY stock. So in this particular slide, as you're noticing here, it shows the amount of material you'd like to leave or stay away from the side walls. In 2-axis machining or 2.5 axis milling, we do not specify a floor stock because the Z, the total depth, is controlled in your cut levels as you specify the depth per cut and the total cut depth. Well, the stock parameters what you specify in the global parameters are the amount of stock you'd like to leave in X and Y or stay away from the side walls. So in this example, we have a pocket operation. So the default parameters on pocketing or facing operations in any of our machining operation dialog in 2 axes, it specifies a stock to leave of about 25 thousandths if you're working in inch units or 0.6 millimeters if you're working in metric units. So I'm going to go ahead and switch to RhinoCam, and we'll take a look at the stock parameters and how this affects our toolpath. So if I take a look at the pocket operation here, under cut parameters, you'll find global parameters, and this is what we call the stock to leave. And by default, it's set to 25 thousandths because pocketing operation is considered like a roughing operation where typically you would intend to leave some stock so you can go back and finish this with a profiling operation. So when we specify a stock to leave, the toolpath, the last path here, as you see, it stays away from the finished edge of the pocket boundary by the distance on all the sides. So let's run a simulation in here and we can visualize it. I'll toggle off the toolpath visibility while it's running the simulation. And also display the part visibility in here. So you can tell by looking at it. So the part region is visible. It's highlighted here. And as you can tell here, we have left 25,000 stock all around the part. So specifying a positive value for the stock will make the resulting pocket cut to a smaller size. If you specify a negative stock offset, it'll overcut the pocket boundary. So going back to the global parameters under cut parameters tab, specifying a stock of minus 0.025 will overcut it. So if you have an application or a need to overcut it, you can specify a negative stock offset and that'll overcut it. The same goes with all 2.5 axis operations, pocketing, profiling, and other methods as well. So in this particular example, you can see that we are overcutting it. I have the part model visible. I can toggle the visibility so you can see the difference here. Now we are overcutting it by 25 thousandths. Now setting the stock to leave to 0 will finish it right to the edge of your pocket. So there's a pocket boundary, and the resulting tool path is right to the edge of the pocket. And the same goes with island regions as well. So if you specify the stock to leave, you would leave material around the island. Or if you specify to put a negative stock, it'll overcut it even on the island region as well. Okay, so the next topic in today's webinar is going to be how to define work zeros and how this helps you establish work origins for machining on your machine tool. So I'm going to go ahead and cover this starting with a slide. Okay, so what is work zero? Work zero could also be known as program zero or work coordinate origin, or in sometimes it's also called as work coordinate offset on how it's represented in different machine tools. So you have your XYZ origin, which is your world origin, and then you have your machine tool coordinate origin. So the machine tool coordinate origin or your XYZ origin for machining is typically called as a program coordinate system or work coordinate system or work origin. So as you place your work piece on your machine table, you would typically do a zero touch off to either one of the corners of your workpiece, or it could be to the center of the workpiece, depending on whatever is easy and feasible to establish the XYZ origin. So to establish this in our CAM program, we would be basically specifying either by doing a work zero, and I'm going to demonstrate that in RhinoCam. So in this particular example here, you will notice that the World Coordinate System origin, also known as the WCS, and the machining coordinate origin are currently coincident. So which means when you first import your part or create your geometry in the CAD system and the origin where the CAD system origin is also by default where the location of your XYZ0 is. So if you take a look at it in this particular model here, this is where we have your XYZ origin. Now, there's a couple of ways how we can establish the origin for machining. One is we can use align and set world coordinate system, where we can transform or translate the origin for both machining and the world coordinate origin to one of the corners of the part, which means this would shift both the part and the stock origin to the location. This would shift to the WCS origin 000. So that would be one of the ways to do it. Now, the alternative way is to leave the world origin where it is and introduce what is called a work zero. So we would be shifting the origin for machining by specifying a work zero, and we would set it to the desired location on the stock. It could be the highest Z, which for the zero face, and for the corner, we could be setting it to the southwest corner, in this case, which would be the lower left corner. So as you take a look at it from the top view, it's going to be the southwest, which would be the lower left corner. And if you look at it from the front view, we are setting it to the zero face to the highest Z, which is the top of the stock. So when this is established over here, you will notice that your world coordinate origin still remains where it is in the CAD system, but the origin for machining or your program zero is now set to the top of your stock and the southwest corner. So this could be called program zero or your work coordinate origin, or we call it work zero in our CAM program. And you could also be calling this out as your work offset, like a G54 or G55, to establish the work coordinate offset. So to establish a G54, you just have to specify the offset register number, which happens to be 54, and your posted code will output the prefix G along with 54. So
Just want to, sorry, I just want to jump in and explain what I mean, in other words, the work zero defines where your origin on the machine is going to be. So where the interpretation of the origin on the machine. So there are two ways, like what I was explaining. Once you set the work zero and you need to, on the machine, touch off. Typically, users will touch off at a corner, kind of like where Uday is pointing to. So we have your stock model sitting on your table. You bring your tool down there and touch off at that corner and zero it at that corner. So that would be your zero or work zero on your machine tool. And that corresponds to this work zero that you define here in our system. So in that case, you're aligning your coordinate axes, if you will, or the coordinate axis origin, if you will. So everything will come out correctly when you machine. And the second thing that Uday was explaining is in some cases you don't need to do that. You set up your work offset and have a G54 come out. And wherever that zero is defined on your machine tool, that's where it's going to use to start machining. So I hope that makes sense.
thank you, Joe. So how the work zero affects your toolpath. So in this particular case, since we set it to the top of the stock in the southwest corner, so all your coordinate program points in your resulting G code will have positive X and Y motions for most part. For example, in this pocket operation, if you take a look at it, here you'd end up with all your positive XY motions because your XY origin is set to the lower left corner and the Z is set to the top of your stock. Now, if I change the location of the work zero, I double click on it and I say I want to switch it to the northwest corner and I pick generate, you will notice that since the work coordinate origin is shifted, all of your operations have flagged dirty, indicating that these toolpaths that I've generated are no longer adhering to the new work zero, which means you need to update your toolpaths, right click and regenerate in order for it to update all of your XYZ coordinates based on the newly defined work zero. So when you make a change to your work zero, the operations underneath the work zeros will be flagged dirty. You'll need to make sure you go back and regenerate it, update it before you post-process your toolpaths out to the machine. So again, I'm changing it back to southwest corner. We'll need to regenerate it. Okay, so the next topic I would be covering here is programming for cutter compensation. And we'll learn about what cutter compensation is and how this works in 2.5 axis operations. So I have a slide for cutter compensation, and then I'll go through a demonstration of how the cutter compensation works in our CAM products. So cutter compensation is used to compensate typically for tool wear, to compensate between the actual tool diameter to the program tool diameter at the machine or the controller. And the cutter compensation is typically output using a G41 to comp on the left, or a G42 to comp on the right, and a G40 is used to cancel cutter compensation. Now, in the following slide here, you'll see we have a profile toolpath for illustration of cutter compensation. The cutter compensation is output on the first linear move on your entry. So in the sample output code, you'll notice that there's a G41 right after your plunge move. At the beginning of your first XY move, you have a G41, a cutter compensation that's being, turning on the cutter compensation And at the very end, before your departure move, it's canceling the catacomb with a G40, and then you have your departure motion. So after the retract, before the departure move, you have a cut a compensation cancel. So in this case, it's outputting comp left. If it was a cut a compensation right, instead of a G41, you'd have noticed a G42 in here. Now there's a few things that I would like to point out for the cut a compensation to work. Number one is your cut direction needs to be set to either climb or conventional. Setting it to mixed will not be able to output cut a compensation. Also, when you're specifying entry and exit, you would need to specify linear entry and linear exit in order for the cut a compensation to work on your machine tool. In addition to these, you will also need to enable cut a compensation in the cut parameters tab, which I will be demonstrating here in just a moment. So I'm going to switch back to RhinoCam to cover cut a compensation. And I'm going to take a look at the 2.5 axis profiling example in here for cut a compensation. So as I edit the operation, I go over to the cut parameters tab, and under compensation, we have the drop-down menu. So selecting to auto none will still compensate, the toolpath still compensates for the tool geometry when the operation is programmed. As you can see here, we're using a 1/2 inch end mill, and the toolpath is compensated by the tool geometry. So in this particular case, there is no catacomb being output in the posted code. Now, setting the compensation to auto on or control on will still compensate for the tool geometry, and in addition to that, it'll also output your cut a compensation code, which could be a 41 or a 42 depending on your compensation right or left. So we need to make sure that the cut direction is either set to climb or conventional, and under entry and exit, we also need to make sure that the entry is set to linear motion under engage motion, and the retract is also set to linear in order for the compensation to be applied. So I'm going to pick generate. And one of the ways you can verify even before you post process the code is you can go into your toolpath editor / toolpath viewer, and you will notice that right after approach motion, you'll see the cut comp left, which is enabling the cut a compensation in here. And I'll toggle off the display of the tool holder, so you can see that the toolpath is still being is a tool geometry. In addition to it, it's outputting the cut a compensation, and right after the departure move, the cut a compensation is being turned off. So as I post process this toolpath, and since we have multiple levels programmed in here, the cut a compensation is turned on for each of the cut levels. You have the G41, and then it cancels out with the G40. This would be for the first cut level, and for each cut levels, it's turning it on the compensation and turning it off. Now, in the case of a pocket operation, the cut a comp is turned on automatically in the final pass. So when you specify your cut direction to climb or conventional, and you specify a linear for the engage motion and generate the toolpath by toggling on the cut a compensation, it'll automatically output the compensation on the final pass for each of the cut levels. So when you post process it, you will see the cut comp being output in the posted code, and you can also notice the same over here in the toolpath viewer. You can see the cut comp is being turned off at this particular level at the final once at the exit motion. So the cut a comp can be applied in several of the 2-axis methods: pocketing, profiling, chamfering, fillet, selecting. The only operation where there's no cut comp would be typically engraving, and also hole pocketing and hole profiling, since these two methods also involve a z-axis motion as it ramps into resulting in a helical motion. In the case of engraving, the tool remains on the geometry, so there won't be an option to turn on the cutter compensation. So this gives you an overview of how cutter compensation works in our two-axis operation. The next topic I will be covering here is engraving and its many applications where engraving can be used in different applications. So I'm going to go ahead and switch to an example to start with for engraving. One of the commonly used applications for engraving is for engraving text or curves or geometries of any shape. So as you have these curves created in your CAD system, or you could import them into your CAD. This could be text or a bunch of curves. As you can see, I have a combination of these in here. So to program engraving, we'll go into two-axis and engraving and select curves as our geometry here. I'm going to just drag a window to select all of these. Right-click and enter to accept our selections. So as far as the tool, you could pretty much select any tool type for engraving. So you could be selecting a ball mill, flat mill, corner radius. What's commonly or typically used is a V mill with a taper angle, which could be a 45 or a 30-degree taper angle like an engraving tool. Or you could be even using any of these tool types in here, including form tools or custom tools. I will be covering how to define form tools later during our webinar today. So we'll specify the tool. We'll set our feeds and speeds, and we'll leave the clearance to automatic. Now we're over in the cutting parameters. You'd want to specify the location of the geometry. So if the curves or the text that you pick is at the top, you would say at top, and then you specify the total depth. So I'm going to specify the total cut depth as 50 thousandths. And you could break this up into multiple levels if you'd like to. So I can split it into two levels here, 25 thousandths each. And when we have multiple cut levels, we could specify the cut traversal between levels either to be zig or zigzag. So specifying zigzag will cut in reverse direction, meaning it goes in both directions. So it'll alternate between the directions for each cut level. And you can control your entry and exit. You can fit arcs to your toolpath in engraving as well. And we can apply a sorting sequence. So engraving can be generated for curves that are open and closed. In this particular example, we have a combination of both open and closed curves. And as you're seeing the cut material simulation, it's cutting it in two levels to a total depth of 50 thousandths. Now engraving can also be programmed for open curves and also curves that are not planar, like 3D curves. And I'm going to go through an example for that also in a moment. So if you'd like to run through the simulation here, you could always select the pause and then pick simulate to end to run through the simulation. So depending on the tool that is selected, you'll see the shape that's formed with the engraving. And with the engraving, the tool tip stays on the part region that you selected as your geometry for engraving. So I'm going to display the toolpath in hidden area so you can see the toolpath. So the tool stays on the geometry that you selected.
Yeah, so I just wanted to add one more to tie this back into the compensation discussion. So you can think of engraving as a toolpath method that does not compensate for the tool radius. All the other methods like profiling and pocketing, they actually take the tool radius into account and compensate by that amount. So the toolpath is actually off of the drive geometry by that radius. And that is by design. I mean, you are using the CAM system obviously for doing that. But in many cases, you don't want to compensate. You actually want to drive the cutter right on the toolpath, right on the drive geometry, and that's what engraving is used for. I hope that makes sense. Thanks, Uday.
Thank you, Joe. So let's look at our next use case for engraving. This could be used for engraving curves or text or any sort of geometry that does not have to be planar. So you may have a sculpted surface and have some text projected onto the surface, and we could use engraving. Even though the engraving is under the 2-axis methods, you will be able to follow along a 3D curve. So I'm going to go to engraving. We'll use select curves. I'll go ahead and select these curves in here. Now you may notice that we have a single stroke font. I'm going to show you how we can avail that single stroke font. We've developed a single line font, and you can download and install it onto your computer, and you can define text using single stroke fonts, and use the project command in Rhino to project those text onto the surface. And now when I specify a total cut depth in here, so I'm going to do a 50 thousandths depth, similar to what we did before. So it's going to maintain the same depth across the 3D curve geometry that you have here on engraving. So as you can see, the toolpath stays on the drive geometry and also maintains the XYZ varies as it follows the 3D curve geometry. So it's not resulting in a planar toolpath. It does follow along the 3D geometry. So this could be one of the very nice use case for engraving along sculpted surfaces as well. Now, a lot of our instrument makers, they use engraving for machining their fret slots. So, you don't have to model the fret slots in your CAD. Instead, you could actually just create those, 3-dimensional curves or the arcs from either the XZ plane or the YZ plane, and use 2-axis in engraving, and just select those curves as your control geometry or the drive geometry, and then pick a tool for it. Now in this case, you could be even using an end mill if you want a 16th inch or an 8th inch slot, or even a ball mill. You could specify that. Specify your total depth in here. I'll specify 25 thousandths. And then we could still fit arcs to toolpath, so this would fit arcs in those principal planes, which could be XY, XZ, or YZ planes. And we now have our engraving toolpath for cutting those fret slots. So I'm going to run a toolpath animation in here, as I've not defined a stock for it, but you'll see it here. So it follows the 3D curve. So just to summarize, engraving can be used for programming open and closed curves. These curves could be 2D or 3D. You could be even selecting surface edges, not necessarily have to be curves. You could even pick surface edges from your solid surface geometry as your part region for engraving. So the next topic we'll be covering today is going to be using start points in 2.5-axis operations. So I'm going to go back and switch to the previous example we were working on. So start points, we'll talk about how start points works in operations like profiling, and then we'll also take a look at how it affects in pocket operations as well. Now, when we program a profile operation, typically it uses the start point of the curve for the location where the entry and exit is applied. Now, when you select a chain of face edges, the start point is applied, is basically utilized from the first face edge that you select for the start point of the curve. Now, in the profiling operation, by default, use midpoint of the longest side is chosen for the location of the start point. So when this box is checked, the start point is determined based on the midpoint of the longest edge, which could have been one of this edge or could be this edge. So in this particular case, it happens to be this particular edge. Now, if I go ahead and clear this checkbox and then generate it, it applies the start point where the first face edge of the curve was selected, or the start point of the curve is selected. So if you're selecting a curve or a curve geometry for profiling, so in this example, I'm going to be selecting a curve geometry, and you'll notice that the start point for the curve is over here. When I generate the toolpath, the entry and exit is applied where the start point of the curve is. Now there's a couple of ways how we can change the start point. One is we can move the start point of the curve that you selected using the CAD tools available in the host CAD system. In this case, it's going to be Rhino. In Rhino, we can change the start point using the command called curve edit tools, adjust close curve seam. You can pick the curve, and you can actually notice that when you select the curve, it displays a point with an arrow, and you can left click and drag the start point to your desired location. So I'm going to move it closer to the origin over here. Left click again, and then right click to accept the start point of the curve. Now, when we made the change to the start point, the operation that utilizes the curve is automatically flagged dirty. So you can see that the control geometry is also flagged dirty, indicating that the toolpath needs to be updated. So right click and regenerate will now update it, so the start point, the entry and exit is applied where the start point is. Now this is one of the ways how you can move the start point. Now, instead of moving the start point of the underlying curve geometry in Rhino, you could change the start point using predefined regions in RhinoCam. So you can create a curve region by selecting the curve. And once you define the curve region, you'll notice that it displays where the start point is for the curve region. And you can use select start point command and pick the start point location. So without modifying the start point of the curve that you built in Rhino, we're just using the predefined regions to move the start point around. Now, once you move the start point of the predefined region, you can select the predefined region in your machining operation by using select predefined region, select it, and generate. So now, based on where the start point that you've set in the predefined region, the entry and exit takes place at the location of the start point. Again, I can move the start point of the predefined region, right click to accept it, and I make the change, right click, regenerate to update the toolpath. Now, this is how we do it in RhinoCam for predefined regions. The same also goes with Visual CAD CAM for predefined regions and all of our CAM products. Now, for folks who are using our standalone Visual CAD CAM product, I'm going to quickly show you how we can change the start point of the underlying curve using our host CAD system in Visual CAD. So once you have your, if you're selecting the curve as your part region, you can also display the curve direction and arrow by going to the options in Visual CAD. You can display it. So that displays the curve direction, start point, arrow. And you will notice that I'm going to switch the view to wireframes. It just makes it easier for you to view it. You can see the start point of the curve is over here. And to move the start point of the underlying curve, you can go to the curve modeling tab and use this change start command, and you can move the start point anywhere along the curve. So I can move it right here, and the start point is now changed to this location. And you can just basically select the operation for profiling and then choose the curve geometry for creating a toolpath. And by clearing the checkbox for use midpoint of the longest side. So if you're selecting the curve as your part region for profiling, you can change the start point by moving the start point of the curve using change start in Visual CAD, or you might by defining a predefined region by selecting the curve region in here and then specifying a start point for the curve region, and then using the predefined region as your curve region for the operation. So we covered how to choose start points in profiling operation. I'm going to quickly go over how we can apply start points in pocketing operations. If you're working with hard materials, and typically you would want to have a pre-drilled hole, so you can use the location of the pre-drilled hole as your start point on a pocket operation. So in this particular example here, I have created a point that is at the center of the hole. And in the pocket operation, I could go to start points and select this point as a start point for the pocket operation. And generating the toolpath will use the start point for the location of the plunge motion and will apply the ramp around the start point. So you can pick start points in operations like 2-axis profiling as well as 2-axis roughing operations. The next topic I'll be covering here is how to control entry and exits.
Uday, before you jump on that, since there were quite a few questions on start points, I just wanted to mention, since all of you are AMS customers, in our 2021 release, which is going to be coming out end of the year or early next year, we have actually changing the way we're introducing a new method for start points for profiling. It'll act very similar to the pocketing. You would be in fact be able to select geometry as start points, and then we will honor that in profiling. So I think it's going to be a really good change. This was implemented based on a lot of your requests. So look forward to that. Thanks, Uday.
Thank you, Joe. So folks, the next topic we'll be covering is entry and exits. We'll focus on 2-axis profiling for the entry and exits. So entry exit allows you to establish how you'd like to enter and leave the material. And in this case, entry and exit basically for profiling is applied where your start point is. So as you go into your entry and exit tab, you could specify the entry and exit. It could be set to lines and arcs, which is typically also could be like a 2D entry and 2D exit if a ramp height is not set. So as you can see here, the approach motion is set to linear and the engage motion is set to linear. So this results in a linear entry, an approach, and an engage motion, and linear for retract and departure mode. Now the entry and exit can be specified for each of the cut levels. And this can be done by selecting apply entry and exit for each cut level in the entry exit tab. Now switching the entry and exit from linear to radial I'm going to just switch it for the engage motion. So you'll notice that after the linear approach, you're going to have a radial entry and then your cut motion, and then we have a linear retract and a departure mode. So depending on the type of entry and exit you're looking to generate, you can choose those options in here and you can specify and adjust the parameters. Now, if you'd like to ramp along at the specified height, you can also specify ramp height in here for the entry and exit parameters. So I can give it a height of 0.25, and generating it will result in a ramped. So in this case, it's not ramping along the path of the curve. It's ramping, entering away from the model here, as you can see, away from the toolpath. So it's entering in. So if you're working with some sort of like a material where there's going to be chipping or involved, so you can basically ramp away from the edge so it doesn't result in any chipping. The same thing can also be set for exit. You can specify a ramp height in here for the exit motion as well. And this would apply for both entry and exit mode. So this is entry and exit using lines and arcs. You also have the option to specify the entry to be along path, where it's going to ramp along the path of your tool path. So if I specify along path, height, and an angle, it's going to ramp along the path, as you can see right here. So there's a ramp motion. Again, since I've said applied entry and exit for each cut level, the entry motion and the exit motions are being applied for each cut level. Now, setting the entry and exit to none will result in a plunge motion, followed by the cut and then a retract. And the plunge is applied for each of the cut levels. There's one thing I would also like to point out here in the entry and exit is there's an option to specify what is called an overlap distance. So if you're noticing any witness mark at the location where you're having an entry and exit, you may want to overrun it by specifying an overlap distance in here. So this will basically go past the start, which results in basically it overshoots it by that amount, so it doesn't leave any witness mark, goes past it by the specified distance. I just use the tool diameter as a distance in here for the entry and exit move. So you can specify these parameters, and you can notice that here the entry and exits are not at the same point. The exit occurs half an inch past the location of the start point. So specifying an overlap distance will allow you to go past it. Now, we talked about entry and exit in profiling. The same also goes with chamfering and other similar type of methods, even facing. Now, the entry and exit in pocketing works slightly differently, where since you're in a cavity, you would want to ramp into a pocket. So you can specify the ramp to be either a path, linear, or it could be helical. And depending on what we choose here, if the helical entry that you specify is not feasible to apply and it's going to result in a gouge, it'll automatically revert to a path entry, path engage motion, which would be the most safest way to enter into the material. So you can notice that there's helical entry motions at these levels, but since it's not feasible to apply helical entry over here, it's applying a path entry even though we have it set to helical, so which is going to be the most safest way not to result in any gouge around the island areas. Okay, folks, the next topic I'll be covering here is how to apply bridges and tabs in profiling. And to cover this, I'll go ahead and bring in a part that's typically commonly done in like a woodworking example. I'm going to bring in this part, which is a deck for a boat or a yacht. And as you can see, we have multiple parts laid out into a sheet, and I've generated a profiling operation for it. So once the profiling is generated, you may want to apply bridges and tabs. So the bridges or tabs, so the part is held intact with the stock material when you run through the final path. So you can go under your advanced cut parameters to specify or establish the type of bridge. We have two types of bridges or tabs we can generate. It could be a triangular bridge or it could be a rectangular bridge. And you can specify the bridge, the height for the bridge and the length and the number of bridges you'd like to insert or create. So I'm going to specify the number of bridges to be 4. So you'll apply 4 bridges on each of these parts. So we have a total of 3 profiles. And the height is specified as 0.15 and the length as 1 inch, the overall bridge length. So generating the toolpath will apply the bridges automatically equidistant at 4 locations. As you notice here, we are applied a rectangular bridge, and you can notice the rectangular bridge is applied on at 4 bridges are being applied on each part. So when I run a simulation, you will notice these bridges in the resulting cut material simulation. So if I rotate the view, you'll see that the bridges are being applied at these locations. Now, when you have a part that's shared with another part, these bridges that are being applied may not be at the most desirable location. And as you can see here, which is very near the edge of the sheet. So you may want to control or specifically pick the location of those bridge points. Now, to accomplish this, we will have to create what is called a predefined region, and we will have to pick out those bridge points or specify the bridge points. So to do that, the first step is we need to go to this predefined regions tab, and we will go ahead and create a predefined region by selecting the curves. I'm going to select the curves. So I'm going to pick the curve, right click. So we define one predefined region. So we're going to repeat the same step for the next one, and we'll repeat the step for each of the profiles. So we now have 3 predefined regions created, and we'll now go ahead and specify bridge points. Now, the bridge points can be done in a couple of ways. We could use automatic bridge points and set the number of bridge points in here. I'm going to set it to 4 and pick OK, and you'll notice that 4 bridge points are being inserted. And you could repeat the same for each of these predefined regions, or you also have an option to specify manual bridge points. You can choose manual bridge points, and you can click the location where you want the bridge points to be placed. So we can do automatic, or we could even do manual bridge points. So in this particular case, I'm going to be placing them over here. So I've placed 4 bridge points on each of these profiles. And once you create the bridge points, you could also move the bridge points. I can just double click, or I can single click on it and move each of the bridge points. I could say I would like to take this bridge point in here and move it closer to this location. Now, rather than having to click on it each time, I can use it in a modal setting, double click to edit so it stays modal, and I can keep moving multiple bridge points in here. I can take this one here and move it right over here. And then once I've done moving the bridge points, I can right click or press enter to accept it. Now that we have defined the bridge points for each of these profiles, I'm going to edit the profiling operation, select remove all, and then use a predefine, and I'm selecting all 3 predefined regions by highlighting the machining region set, accept the selections, and then generate. You will now notice that the bridge points are created at the location where you have these defined on each of these profiles. So by doing so, you'll be able to control precisely where you want those bridges and tabs to be. And when you run the simulation, they'll be at the exact same locations where you created them. So this is how we can define bridge points at the desired location and select the predefined regions for establishing your bridges and tabs. Joe, I'm afraid we are running a little bit over time. Would you like me to cover the other 2 topics or defer it to another webinar?
Yeah, I think we can quickly cover that. And then we have a few more topics that that has come up during this webinar with the questions that we can squeeze into the next one. So if you want to go quickly run through it, that'll be good.
Okay, I'll certainly do that. Thank you.
Thank you.
So the next topic I'll be covering here is how to create and utilize user-defined tools. And to demonstrate this, I'm going to go ahead and take this example of a table here where you can see there's a profile that follows around this table. And this is a custom profile that I would like to machine, but I don't want to use like a ball mill or a corner radius tool. We have a special like a custom profile cutter that you may have built, and to take advantage of that and be able to cut it in 1 or multiple XY passes, you could have a tool that's modeled which represents the form of this profile. So the steps to create it is, first, I'm going to go into this layer tree to hide some of these features in here just to make it easier for us to see it. So the first step is you need to model one half of your tool profile with the tip at the origin. So you model the cutter profile that you'd like to use to define as a form tool or a user-defined tool. You highlight or select it, and then you go into your tool, create edit tool tab, select user-defined mill, and then select load selected tool profile. So the tool with the profile that you created, the tool is defined, you can save it as a new tool. Now once you have a tool defined, the programming would be very similar to how we programmed a profiling operation. So you go into 2-axis and profiling, you pick the tool. In this case, this would be a user-defined tool. Establish your feeds and speeds and clearance. Then we choose the cut side to be on the outside. And for the cut level, since I've chosen the curve at the bottom edge, I'm going to leave it as at bottom. Set my entry and exits, and then generate the toolpath. So this is going to cut this profile in one single XY pass. And as you notice, the cut material simulation also shows the user-defined tool and the form that it creates. If you'd like to step it in multiple XY passes, you could always edit the operation, specify a total cut width in here, and you can run it in one or more passes. So that would be your first pass. You don't take up too much load on the tool cutter, so you can step it in by using multiple step over passes. So there are several different applications where you can use user-defined tools for. You can use them in 2-axis profiling and in engraving as well. So the last topic we have today is fixture offset programming. And I would like to start that by covering it with a slide here. So let's talk about fixture offset programming. So when you have multiple parts that are sitting on multiple different vices on your machine table, and each of the parts or each of the material that you have their own origins established, we could program these very efficiently and easily in our CAM program using fixture offsets. So for example, in this pictorial representation that you see here, we have 2 stock planks, and each of them have their own origin location. So this could be called your work offset number 1, represented by G54, and this could be work offset number 2, which could be G55. So rather than having to program each of these and then manually changing or editing the program to do it, we can do this programmatically and automatically in our CAM program using fixture offset programming. So I'm going to go back to this example, and I'll take this chamfer operation and consider that we would like to run the chamfer operation on using multiple fixtures. So to accomplish this, we would want to go into create miscellaneous operation and select fixture offsets. Now you specify the first offset number. So if you're starting with G54, you specify the 54, and then you could specify how many additional fixtures that you have. So if you have 3 fixtures, I want to specify the repeat count as 3 and the increment. So if you need G54, 55, and 56, the increment would be 1. If you need 54, 56, and 58, the increment would be 2. So I'm going to set it to 1. Repeat count is 3, so we have 3 fixtures. And then I'll pick generate. Now this introduces a fixture offset folder, and I would have to just move the operations that I would like to apply these fixture offsets into the folder. So just drag and drop. Now this is not going to show the offsets in the toolpath or in the simulation. It only applies in the posted code. So when we post process these, you will notice that your instance number 1 is a G54, and then your instance 2, G55, In the final instance, G56. So since we said the repeat count is 3, we have 3 fixture offsets, 54, 55, and 56. So you can have one or more operations programmed under each of these fixture offsets. With this, I would like to conclude my part of the presentation and hand this back over to Joe.